Team, solubility equilibrium is one that we just glazed over last year because it is not easy, but we are going to tackle it, and I'm going to try to do it as succinctly and as easily as possible, being that I've improved on it from last year. So, as a teacher, let's go to solubility equilibria, an equilibrium between a precipitate on the bottom and dissolved ions in the solution. You can't include a solid in your K calculation. So we've learned about that. And basically, we have a solid sitting in a beaker here that's going back and forth between being a solid and then dissolving, and then it's kind of going back and forth and doing this back and forth thing. And when it dissolves, it breaks down into the ions. So often it's the larger ones are the positive ones. So we've got Ba2+, and then we have these smaller SO4s that are kind of going back and forth. That's what's happening. We have one Ba, we have one SO4, and so it's one solid breaks down into two different ions. And so we've got our K as P, we have our concentrations. And then if you have what that concentration is, let's say for instance, they give you KSP is equal to 1.1 times 10 to the negative 10th. Okay, and if we have, just like our previous K values, K SP is, it basically means the solubility product constant, so how soluble is something. If it's less than 1, it's not very soluble. If it's greater than 1, it's way more soluble. Okay, so if we have a KSP value that's really high, it's going to break down and move to the right into these different ions, and it's going to dissolve and there'll be very little left over. If we have very small values, then it's going to be reactant heavy, and therefore it's going to lean towards staying in a solid state, but some is going to dissolve. All right, solubility equilibria. Solubility is measured in grams per liter. I haven't seen very many problems do that. Molar solubility is the same as molarity. So it's moles per liter. When comparing solubility, each equation must produce the same number of ions. You can't compare solubility. If not, you can't just compare using KSP. Let's see if we have the example of that coming up here. Oh man, let's delete that. I've got a duplicate slide there. Sorry about that. Okay, which is more soluble? Which can I not compare? All right, so I've got on this, the first question will be on this first half. We have AgCl, AgBr, AgI. So there's one positive ion, one negative, 1, 1, 1, 1. So because there are no subscripts, we can compare these. It's one thing breaking down into two different things when we dissolve it. And so let's compare which one is more soluble, which is more likely to move from the left to the right and be broken down. That value is measured as K. So the largest one is 1.8 times 10 to the negative 10th, which is exciting. We've got that portion right here. Let me see if I can, let's see what we can do here. So that's this guy right here. I am going to change this to be transparent and change my line to be red so that you can kind of see that. There's my answer. Okay. All right. And for the next one, which can we not compare? We have to decide, is it going to be AgCl or PbCl2? How many ions are we breaking down here? Okay, so on the first one, on this half, we start with one molecule for AgCl, but on PbCl, we have 3 molecules, okay? Sorry, no, that's, what am I saying? That's one molecule as well. PbCl2 is one molecule, okay? All right, but then if we come over here, let's do this, let's move that over here. For the top one, we have 2 different ions, or in effect, we have 2 different molecules. But we have one Pb, okay, because there's one coefficient there, and then we have 2 Cls. So we have 3 molecules on the bottom, okay? And because we have 1 going to 2 and then 1 going to 3, we cannot compare these. It is not possible for us to compare these ones. All right, let's head over here. Look at the mole ratios. Missing one concentration. Okay, if something is at equilibrium, then there is exactly double, triple, half of the other ions. So if we're already at equilibrium and they gave you the value, you can look and just use the mole ratios and be like, okay, if I have calcium is 2.1 times 10 to the negative fourth, to be able to find the F value, all I need to do is double the value of Ca, and I can put the F value in there, okay? And, oh man, let's see here. Okay. Oh, this one was intense. I remember we did that one on the board. I wonder if I could. So example of calculating the solubility. So we need to find a moles per liter, molar solubility, okay, of CaF2. Okay, and this is going to be write out the balanced equation, make an ice table, set equal to KSP, and solve for X. Okay, I'm going to make a new slide, and we're going to do this one together. Okay, so let's go for it. We're going to start with Ca2F, okay, which is in its solid form. Okay, and let's make these smaller. There we go. Makes it a little clearer. Okay, and then we're going to, and I will simplify. There's my equilibrium symbol because we're going both directions. I believe there's a character. My OCD is kicking in here. Let's see if we can find the character for equilibrium. There it is. I don't know what this character is called, but there we go. We got it. Okay. All right. All righty. So we've got CAF going to 1 Ca2 plus, and that Ca2 plus is actually just to indicate that it's an ion. Okay. Plus 2F minus. And that F minus, the minus is also just indicating that it's a negative. Okay, so once again, we have one thing breaking down. Why is that 2 there? That 2 is in the wrong spot. I apologize, team. That should be CAF2. That makes more sense. Whew, that was scary. All right, so I've set up the first part. Like I said, drawing this out on the board would have been a lot easier, but we don't have time for that right now. I'm asking you guys to learn from home, and without that ability, it's tough. Okay, so initially, and once again, we can't use this S in our calculations. Okay, and I'm even going to just get a little extra and strike through that. Oh, I can't, it doesn't let me strike through the S. But we're going to say, okay, to start with, I have 0 of this, and I have 0 of this. Okay, those are what I've got 0 of. But then for my second line, I'm like, okay, we're going to add x plus x for what changes. And this one, because we have the 2 in the front, we have to add that 2 to whatever the change is here. And that means that our equilibrium value is going to be x, and then we have 2x down here. Okay, so there we go. Now we can calculate the KSP. KSP is equal to x times 2x. Okay, but the other thing we need to remember is to square it. And this is where I made a mistake this weekend when I was working on this, because I forgot to square that value. I'm going to highlight that value to remind us to square it. I'm going to highlight this one to remind us to square it, so that we're doing all of those things we need to do with that coefficient. Okay. Oh, and I thought we'd have to turn that off. Turn that one off to transparent. Perfect. Okay, so now I can say, well, the KSP value that they gave me in the problem was, and that's in the previous problem right here, 3.9 times 10 to the negative 11th. Okay, so I can say, okay, my KSP value, I think I'm still, there we go. KSP is equal to 3.9 times 10 to the negative 11th. Okay. And I can now set these equal to each other. I can say, oh, here we go. I can say x, so it would be 4x cubed is equal to, and then I can do 3 point, and I hope that you guys can see I skipped a step. X, and then all of this together becomes 4x cubed is equal to, and I've just set them equal to each other. And now, with a little bit of fancy algebra, okay, and if you don't know how to do that algebra, please come see me. Our x, and we have to do a cubed root to both sides, by the way, guys. So I'm not sure. Let me see if I can insert a character to tell you guys to do that. Cubed. No, it's not going to root. There we go. We got it. Perfect. Okay, so I need to cubed root both of these to be able to get to my answer. There we go. If I can cube root both of these, then I can get an x value, okay? And I would of course, have already divided by 4. So let me show you that work really quick. Go Control Z. So I started here, which means I would divide both of these, divided by 4, okay, and then I would take this side and I would divide it by 4, okay, to be able to get rid of that. And so now I have 3.9 times 10 to the negative 11th, that value divided by 4. Man, let me grab my calculator so you guys can see my work. I know that that helped me when my teacher would show that to me. And some of you can skip all these algebra steps, and you have my applause if you can do that. This is me just trying to break it down for people who maybe don't have as much algebra experience. Okay, and so then we have right here, this is going to be the cubed root of that. And then we've got this value is 9.75 times 10 to the exponent 12. Okay, and then we take the cubed root of that. Second. So I click on the math button, then click number 3. Okay. Oh, sorry. My bad, math 4. Math 4. And my x value that I'm getting over here is x is equal to 2.14 times 10 to the exponent negative 4. That's what I'm getting for my x value, which in this case is a concentration, which is m, or moles per liter. That is my answer, team, and I'm checking it right here. I'm scrolling through my notes. One place that you guys can check to see if I have answers on the lectures are in the notes, the lecture notes. And yeah, we got it. It's this one says the answer is 2.1, and I'm grateful that it's correcting me on that, because I would have put 2.14. And here they only have two significant figures, so my answer is going to be in two significant figures, 2.1 times 10 to the negative fourth. And there it is. So I'm going to highlight that in a light green color to show you that's my final answer. But that's how I set this up. I got my KSP from the ICE table. I set it equal to my other KSP. I solve for x, my x value, how much the equation changed. That x, okay, is what my molar solubility is, or how much does my solid dissolve. That's another way to talk about this, is saying, okay, the measurement of how much my solid dissolved. Okay, there we go. And I can, there we go, the measurement of how much my solid dissolved. There we go. So that is what molar solubility is, team. And we calculated it. So that was tricky, that wasn't easy. Let's move on to precipitate. Whew, this one was also not easy, but let's tackle it. On the precipitate page, ooh, I did it on a whole separate page. Okay, and that was when I did it on the, okay. So let's see here. Thank you for your patience, guys. When it's asking us, will these two things form a precipitate? The first thing that we need to do is we need to say, okay, what is this going to make? And what it's going to make is we have a double replacement reaction. So we're going to get PB, and then we're going to have SO4. SO4. And the charge on PB, I can tell right here, is a 2+, okay? And it's going to be a 2+, and SO4 is a 2- because Na is a 1+, so SO4 has to be a 2-. So if it's a 2-, then they cancel each other out, and it's just going to be PbSO4, because the charge on Pb is 2+, the charge on SO4 is 2-. They cancel each other out, and we're good. So that is my first step. And then on the products, and then the other one is going to be NaNO3. And Na has a charge of 1+, NO3 has a charge of 1-, therefore they cancel each other out, and we are good to go. Okay, we are good to go. And all right, here we go. The next step is we need to decide which one of these is going to be a solid. Is lead sulfate going to be a solid, or is NaNO3 going to be a solid? And team, I'm going to cheat and tell you guys something right now. Anytime that you guys see NO3 hanging out somewhere, if you see NO3 hanging out somewhere, NO3, okay, there's a hard and fast rule, will never form a solid. I can't think of an example where NO3 as an ion mixed with something and formed a solid. So therefore, I know for sure that this is going to be aqueous. The other thing that I know is that PbSO4, okay, PbSO4, lead likes to form solids. I know that because I've seen that a lot in chemistry. You guys don't know that, but lead likes to form solids. So if you see this and somebody's asking you and they're like, hey, is one of these going to form a precipitate or a solid? You can look at this, finish the double replacement reaction and be like, oh yeah, it probably will, and it's probably going to be lead. Okay, so here we go. I used to have a big thing of lead precipitate in my back room that we couldn't get rid of. It was bright yellow. Let me see if I can find some on the internet to show you right now. Lead precipitate. Okay, what do we got? Do we got any? Oh yeah, it's that nice bright yellow. Let me see if I can get some images there. So you can kind of see a lead precipitate is this really cool yellow. That's the one we like to use in chemistry the most. But the problem is it's really hard to dispose of. And so we've stopped using it in DODEA schools, but it's a pretty cool chemical to work with and look at. So anyway, I'm just sorry that's something that we can't work with in the lab. Let's rock and roll. So now that we've established that we know that our precipitate is going to be Pb, right, SO4. That's what we know. And it's going to then have the, I'm going to steal this character from before, Control C, Control V. I'm going to blow this up a little bit. I'm going to change my overall font back to black. Okay, so I have PbSO4, and it's going to turn into a Pb ion, which is 2+, and an SO4 ion, which is 2-. Okay, and I'm going to put these where you can see them in the right places. All right, PbSO4, and then yep, there we go, we got it. So the question then becomes, okay, we got PbSO4. Our question then becomes, all right, how do we calculate the initial, how do we calculate the KSP for this? And the way that we can calculate that is if we look here at the next slide, we've got what we just did before. Our KSP value is Pb is equal to SO4. Pb times SO4. That's all we can do. Because it's a solid, we can't use it in our calculation. And so the question is our K value going to be greater than our KSP value? And on here, I'm trying to see if they gave us a KSP value. And I don't see a place that they did, okay? And so it's hard for us to finish this problem and do the full calculation without more data. And so I'm not going to have us do that, and that's why initially it seemed like maybe it was a little confusing, okay? But we have to do a calculation to be able to show how does our KSP versus our Q line up. And team, I will get back to you on this.